Hi there, my name is Raymond Doe, and welcome to my Physics 2212 Lab 5 video, Magnetic Braking and Faraday's Law. I hope you enjoy. The purpose of this lab is to not only visually observe the physical interactions of magnetic fields due to Faraday's law, but also conceptually understand and compute its atomic effects. To accomplish this, we will collect the observational data of a magnet falling through a conductive tube of aluminum foil and model the magnet-tube interactions computationally, and then finally compare my computational predictions with my observed data. Some of the fundamental physics concepts we would need to know in order to implement them into our experiment includes Faraday's law, magnetic flux, the Biot-Savart law, Newton's second and third laws of motion, and Lenz's law. This slide simply shows a preview of my results with my computed simulation of the bar magnet's velocity to the left and the average time it physically took to fall through the aluminum tube on the right. As you can see, the computed time of the magnet's descent is shorter than the observed time. We'll explore why later in this video when we discuss the event of magnetic braking. Here I have listed my initial conditions, with the system being the bar magnet in the aluminum tube, with the surroundings being the surrounding environment. Following that, I have described the general procedures for both the observed experiment and the GlowScript computational portion of the experiment. With these tasks and variables clearly established, let's get to my data. For the observed experiment, I simply took my bar magnet and dropped it through a vertically oriented aluminum tube and recorded the time it took for the magnet to pass from one end of the tube to the other. I ran this procedure 5 times, and using Excel, I calculated the average time it took for the magnet to pass, with that value being 1.24 seconds. Moving on to my GlowScript code, I believe it's important to break down each section of the code so as to fully understand how the simulation is formed. So here I have my constants and initial conditions that I established earlier. Here we have the calculations of the bar magnet's magnetic field using the Biot-Savart law and its magnetic flux, and the total magnetic force exacted onto the tube. Finally, in generating our velocity and time graph, we simply use the net force equation you see above and the basic kinematic equations for position and velocity that we learned in Physics 1. And here we have our resulting velocity time graph. Initially, the velocity of the bar magnet decreases sharply as the force of gravity is stronger than that of the magnetic force. However, after approximately 0.1 second, the induced magnetic field of the tube strengthens and equilibrates with the force of gravity, causing the plateau region on the graph. Finally, as the bar magnet approaches the bottom end of the tube, the force of gravity begins to retake control as there is less magnetic force towards the ends of the tube. This is represented by the sharp decline around 0.8 seconds. And beside our velocity time graph, we have our visually simulated aluminum tube, with the blue regions representing clockwise current and the red region representing counterclockwise current. These conflicting currents cause the magnet to fall slower, which we call magnetic braking. The shorter time displayed in the computed model than the observed model can be attributed to the negligence of air resistance from our assumptions. We have two what-if proposals in this lab. Firstly, what if the resistivity of the conductor were reduced as close as possible to zero, and how would the dynamics of the falling magnet change? Due to the inversely proportional relationship between the resistance and current, the act of reducing resistivity will result in an increase in current. This concept is supported by the Ohm's law and its formula. Secondly, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, holes or slots being put into the aluminum tube would serve to reduce the amount of magnetic rings the bar magnet would have to induce, and subsequently cause it to fall faster, as the magnetic force keeping it afloat would decrease. Thank you for watching and have a great day.